Hello everyone, I'm Rohit Gupta and I'm going to be presenting my paper Open Vocabulary Multi-Label Video Classification. This paper consists of research work done during my internship at Amazon along with all of my collaborators. The key motivation of this work is to build a strong foundation model for video classification. This model should be able to recognize a wide range of concepts such as objects and actions. And this model should also extend to the open vocabulary setting. Since collecting training examples for all possible concepts is impractical, an open vocabulary model fulfills an important need. Additionally, this model must be multi-label since we need to label videos comprehensively. Though our work is related to prior problems such as zero-shot image classification and zero-shot action classification, it is a significantly more general task and covers a much wider range of semantic concepts. Taking a look at some prior related works, CLIP can be utilized as a foundation model for image classification by ranking labels. As CLIP is trained contrastively to align image and text modalities, the similarity of the feature space between image and text can provide a good measure of semantic matching. This similarity score can be used for classification. So the first step towards creating this classifier is to pass the names of the class labels through the text encoder and obtain embedding for each of the labels. These embeddings can then be matched to a given image in order to carry out zero-shot classification. However, CLIP has certain limitations which make it unsuitable for the general task of multi-label open vocabulary video classification. Starting with the first limitation is the ignorance of concept hierarchy in CLIP. CLIP's understanding of semantic relationship between labels is poor because it's trained purely on image caption data. It doesn't, for example, CLIP does not understand that a bagel is a type of a bun. Essentially, when we take a image of a bagel and we use CLIP to rank the labels bagel and donut, it successfully recognizes that this is the image of a bagel. However, when we ask it to compare on a coarse grained category task, like for example comparing a bun to a dip, it's unable to recognize that the image of a bagel actually belongs to the class bun. Secondly, CLIP is unsuitable for the task of multi-label classification because the CLIP scores provided are uncalibrated. Essentially, in CLIP, we rank the labels, whereas in multi-label classification, we actually require a well-calibrated absolute threshold for label classification, and ranking the labels is insufficient. We illustrate this by trying to classify videos from two different data sets. So in this case, action data set and object data set. And we find that the optimal threshold for multi-label classification using CLIP is completely different for these two data sets. This is because the threshold for CLIP is not calibrated in an absolute sense. And the set of classes and even the formatting of the class names can change the optimal threshold. Finally, the most crucial limitation of CLIP for the task of video understanding is that CLIP lacks temporal modeling. So understanding actions and videos requires modeling the video's temporal dynamics, but CLIP is obviously as an image model not trained with any temporal dynamics or temporal attention in mind. Off-the-shelf CLIP has achieved significantly good performance in some video classification tasks. However, this uses an average pooling setting and it cannot succeed in tasks which require temporal understanding. And this essentially limits the action recognition performance. So this can be illustrated in this synthetic tasks such as in a video of a red and yellow circle appearing in order, CLIP is unable to recognize which order it appears in. Looking at some other related work, some recent works have attempted to utilize LLMs to remedy the limitation number 1 of CLIP. Essentially, these methods prompt an LLM to generate some additional descriptors for CLIP. For example, in order to classify images of a hen, they prompt the LLM to generate visual features to distinguish hens in a video or in an image. The LLM generates some descriptors such as feathers, legs, beaks, and so on. And these descriptors can be used to enrich CLIP prompts in order to improve classification. This method is illustrated on the right. Moving on to a discussion of our approach. Our approach has three key points of novelty. First of all, we leverage an LLM to boost the text understanding of CLIP. Secondly, we create an end-to-end learnable architecture in order to get strong, well-calibrated multi-label classification scores. And finally, we add a temporal modeling to the CLIP vision encoder in order to fix all three limitations of CLIP. Here is a look at the detailed system figure for our method, and we'll dive into each part of our system part by part. Let's look at each part of our system. As overall, our system has three components: learning to prompt, the hybrid label encoder, and temporal modeling. So first of all, let's look at the learnable prompting architecture. So the goal of our system, this component is to actually generate strongly useful classification prompt for clip text encoder. Here, learnable prefixes and text prompt asking the LLM to generate useful labels for distinguishing a class in images is input to the LLM. And finally, the LLM generated tokens are converted into a format suitable for prompting clip. These tokens are passed through a prompting transformer in order to transform them into the clip input space. Once these tokens have been transformed by the prompting transformer, they are input into the clip text encoder along with the class label. And this overall label encoder consisting of the LLM and clip is used to generate a strong label embedding. So this label embedding has been enriched with the world knowledge and reasoning capabilities of the LLM and the visual grounding capabilities of the clip text encoder. Secondly, we come to the video or encoder branch. So on this side of clip, we in order to convert the clip image encoder into a clip video encoder, we attach a temporal modeling branch, which is lightweight and parameter efficient. This visual branch generates a video embedding, and this overall system can be trained end to end by utilizing a classification loss on matching the label embeddings to the video embeddings. We further provide some more details about our temporal modeling branch. So this is a parallel branch to the main network in order to avoid fine-tuning the bulk of clip image encoder and losing generalization. And additionally, this temporal modeling branch is augmented with a temporal attention layer, which is similar to a transformer style factorized attention. And this we also in these spatial attention layers in the temporal branch are initialized with the weights from clip, and additionally stochastic weight regulation is applied to the spatial attention layer to preserve generalization while the temporal attention layers are fully trained. Here's a look at the parameter counts and the parameter efficiency of our temporal modeling layer, which only consists of additional 12 million parameters trained from scratch. Here's a look at our loss function. As this loss function is calculated between our label embeddings and the video embeddings. So we have for a given video, let's say we have three positive labels. Then a bunch of negative labels are sampled from our large vocabulary, and dot product is calculated. So this dot product provides us the clip similarity between the labels and the videos. In order to perform loss calculation, these similarities are then sharpened, and a weighted cross entropy loss is applied with respect to the ground truth. We find that the sharpening operation improves our training. Here we illustrate the three different stages of deploying our open vocabulary classification model. In the first stage, which is training, the prompting transformer and learnable prefixes on the label encoder side are learned, whereas on the video encoder side we learn the temporal modeling branch. After the training is finished, in order to expand the vocabulary for our classifier, we pass new labels through the LLM and then the clip text encoder and obtain additional label embeddings. So these additional label embeddings can be stored, inferenced once and stored in order to add additional labels to the vocabulary. And finally, during inference, we pass a video through the our video encoder in order to obtain the video embeddings. These video embeddings can then be matched with the known label embeddings in order to classify them into classes. Here we discuss some of the baselines that we propose to compare our model against, as this is a new problem that we are proposing. So first of all, we look at training free approaches. So training free approaches include baseline clip and then clip plus LLM generated descriptors as discussed previously. We additionally look at clip fine tuning based approaches such as Wi-Fi clip. We also look at text prompting based approaches such as co-op, which has learnable clip prompts, or dual co-op, which has learnable clip prompts for multi-label classification. Here is a brief look at co-op and dual co-op methods. Coming to our experimental setup, for the training set, we combine YouTube 8M and kinetics videos. This gives us a good mix of object, action, and scene labels. and these dataset contain at least one label per video, and YouTube ATEM typically contains 3 labels per video on average. And for our test set, because we aim to have good open vocabulary performance, we have both supervised test set from YouTube ATEM and Kinetics. We also have open vocabulary test set for each of our tasks, such as for action classification, we test on ActivityNet. For object classification, we test on TAO dataset. And for mixed setting, we test on React, which combines object and action. Next, we go to our results section. Here's a brief overview of results. First, we'll look at benchmark results. Then we'll move to examining the score calibration performance of our model. And finally, we'll look at some ablations of the temporal encoder, label encoder, and so on. First, let's look at the results for the training-free baselines. So as we see these baselines, we actually provide the area under the precision recall curve metric for multi-level classification. This is a threshold-free metric which provides a good measure of the reliability of the model. As you can see, these models are reasonable at some datasets, but not so good at action datasets. Next, we look at the learnable or trainable baselines, such as co-op, dual co-op, and Wi-Fi clip. These methods do not provide a significant boost over the training-free baselines. Finally, coming to our method outperforms both frozen and trainable methods in both supervised or closed vocabulary as well as open vocabulary settings across all datasets. Next, we come to the question of calibration of the scores predicted by our open vocabulary model. In this figure, we compare we plot the F1 score against the chosen threshold for both supervised or closed vocabulary and open vocabulary datasets. We find that our model is much more robust to different choices of threshold than the training-free baseline. This is a result of our end-to-end training, where we put the LLM and clip in this into end-to-end training manner, and that allows the model to become well calibrated. Next, we look at some ablations for our temporal modeling layer. So in the first ablation table here, we find that the optimal number of temporal modeling blocks is 4. And secondly, we also look at our attempts at regularizing the added parameters for temporal modeling. And we find that the use of our spatial regularization and freezing the clip backbone results in the best trade-off for open vocabulary performance. Next, we carry out the ablations of our label encoder. As our label encoder consists of a clip text encoder and LLM combined, it is important to justify why both of them together play an important role. We find that if we remove either the LLM or the clip text encoder, our models underperform on the open vocabulary setting. And this illustrates the importance of using the LLM to enrich the label embedding with world knowledge, and also the use of clip text encoder to generate embeddings grounded to the visual setting. In order to further enhance our results, we also explore the use of foundation models such as LLMs and multimodal LLMs to enrich our training label vocabulary. So we pass our videos through multimodal LLMs such as IDFix and Lava to generate captions for the videos. And we use a text LLM Llama to extract object and action labels from these generated captions. Then using a clip text encoder, we cluster these different newfound labels in order to extract base class names. Since these captions contain many variants of similar class names, this clustering step is crucial to reduce noise. As a result, we are able to obtain a ton of new labels. The next step is to take our additional enhanced vocabulary and use our foundation models to assign these additional labels to videos. So for a given video, we once again obtain the captions and use the clip text encoder to match the extra vocabulary labels to the videos using a threshold on the clip similarity. Here we illustrate some of the clustered labels that we generated. So, for example, we identify a number of additional labels in the airline area, grilling, topic grilling on Lego, playground, and then video games, water slides. So, this synthetic process really enriches our training data with lot of fine grained, thousands of fine grained. We call back our results again. So here we show that the use of these synthetic labels during training significantly enhances our performance. In particular, it significantly boosts our performance on action understanding on ActivityNet by 3% and on RearAct by 1%, and on object understanding also it increases the performance by almost 2%. Here we show some qualitative results from our. Here we summarize our findings and contributions so far. We trained a single model which is capable of multi-level action and object classification. We proposed a novel method to combine the visual recognition capabilities of CLIP and the language understanding capabilities of LLMs. We successfully integrated CLIP and LLM end-to-end in a single training loop. We outperformed state-of-the-art open vocabulary classification baselines across known and unknown classes. Thank you for listening to this presentation. Please feel free to send any questions to the authors.